Okay, in this video I'm going to continue on with my tutorial series on thermodynamics and statistical mechanics. This is video number 25 and I'm going to discuss the second law of thermodynamics. Before I do that, the videos previous to this are as follows. Number 1, my very first video, where I discussed the meaning of heat and temperature. So you need to know what temperature and heat are in order to understand this video. Next, I did a lot of videos, but the most important of which are numbers 21 and 24, where I discussed the sharpness of the multiplicity function. What we saw is as follows. We saw that when you have two solids together, solid A and solid B, that each of those will continue sharing energy until the multiplicity function has gotten to its maximum value. And I'll speak more about that in a moment. And we saw that when we plotted the multiplicity function, we saw that going from here down to the end was an absolutely, you couldn't plot it on paper if you even wanted to plot your multiplicity function to be this particular size on paper. So this would be this would be thousands of kilometers on paper, or if this is only a centimeter. So the point is, the multiplicity has increased and it's ridiculously likely that it's going to be in that particular state. Anyway, so I'll speak more about that in a moment. Now the point here is that this video is standalone and I will explain everything, and you don't actually need to have seen the previous videos. So bottom line up front, the second law says that heat flows from hot to cold, which can be said that, paraphrased, that multiplicity tends to increase, or that entropy tends to increase, or that disorder tends to increase. Now in my next video I'm going to discuss entropy, so for that reason I'm not going to discuss the entropy or disorder here, but I put them there for completeness. Now, so really what I'm going to discuss in this video is that heat flows from hot to cold and multiplicity tends to increase. Now, if you are following my tutorial series, we have actually seen the second law numbers of times, but I've never called it that so far. But now I'm going to actually discuss it. So what did we see? We saw the following. When we analysed ideal gases and Einstein solids. So an Einstein solid, by the way, is just a first approximation at the energies in solids. It's not very important. But what we saw is whether you have an ideal gas or you have a solid. Let's say you have two systems, A and you have system B. Okay, and before I talk about system A and system B, let's just say what temperature is. Temperature is a measure of something. It's a measure of your body's willingness to spontaneously give up energy. And the energy it gives up is heat, or if it's cold, the energy that it gives up, or the energy that it takes in, is heat. So that's important. Temperature is the willingness of your body to spontaneously give up heat. So a hot body, which is high temperature, will like to spontaneously give up energy, and a cold body, which is at low temperature, will spontaneously receive energy. So like I said, let's go back. We had two systems, say A and B. Let's say they're two ideal gases or they're two solids, and each of them we'll say Q sub B units of energy in B and Q sub A units of energy in A, and each of them has their own multiplicity, the multiplicity of B and the multiplicity of A. Alright, now, so for those who haven't seen my videos before, what does multiplicity mean? Multiplicity, which is given the placeholder, I give it the placeholder omega, is the total number of states. So I think the quickest way to explain this is if you think of an atom. Let's say each of the atoms say your atom has 3 shells, okay? And in those 3 shells, this one has 3 subshells, let's say this one has 4, this one has 3 subshells, and this one has 2. Well, if I'm an electron, how many different places or how many different states are available for me? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this particular random case, the multiplicity is 9. But you can imagine for an ideal gas with Avogadro's number of molecules, which is, well, I can't even remember, 10 to the 26 or something like that. Anyway, when you have billions of molecules, you can imagine that the multiplicity is going to be absolutely enormous, because it will be made bigger by the number of particles, the number of energy, the amount of energy in your system, the volume and all this sort of thing. So we're talking about a massive number. But anyway, so going back to our system here, we saw that when we had Einstein solids or ideal gases, if we put them two systems together, that they will share energy. That's what we saw, but we didn't really know that yet, because we said that, let's say that Q sub B is greater than Q sub A. So B is hotter than A. Well, just by knowing that B is more energy and therefore is hotter, we can say, well, as a result it's a higher temperature and it's going to give up energy. And A is at a lower temperature, so it's going to want to spontaneously receive energy. The question is, when does this spontaneous flow of energy stop? Okay, well, it stops, you might say, when it's in equilibrium, and we know it's just by our our kind of intuition. We'll know that it'll stop when both bodies are at the same temperature. Okay, that's what equilibrium is. But when we discussed Einstein solids and ideal gases, we could mathematically prove this, because we found that the total multiplicity, we'll say, is the multiplicity of A multiplied by the multiplicity of B. And written in this form, it's not very good to us. We weren't able to see its physical properties just by looking at the formula. But I showed in previous videos that we could arrange both of those as a maximum multiplicity multiplied by some Gaussian function, G-U-S-S-I-A-N. So that the total multiplicity looked something like this. If I plotted the multiplicity of solid A, there's the multiplicity, and I'm just looking versus Q sub A, the amount of energy in A. What we found was that at the end, or at a later time, the system would look like this. Okay, it would look like this, and it would say that, let's say, if we were to draw, just to talk about scales, if I was to draw from here to here on paper, properly I would need thousands of kilometers, but if I draw from here to here, I would only need a centimeter. But what this means here is that if the energy in A, after a while, after sharing energy with B, the energy, we'll say this energy here will have a zero. It has zero multiplicity, so it's pretty much. So it won't be in that state. This is zero multiplicity, 0, 0, 0, 0 multiplicity. So the system will not be in any of these states. It won't be in any of these states either, and there are, as I said, like billions of these states. But instead, the system is most likely going to be in these ridiculously small few states here, where the multiplicity is going to be absolutely enormous. Okay? Going to be an absolutely enormous number. So we found that the system's after settling down into its most likely macro state. But when we looked at the energy, at what energy will it be when it's in its most likely macro state? It'll be when it is exactly the total energy over 2. So this is Q sub A, and this is the total energy over 2. So the system will stop sharing energy, or be in its maximum multiplicity, when it has exactly half the energy, when there are, of course, 2 bodies. Or it'll be a third of the energy if there are 3 bodies, or a quarter of the energy if there are 4 bodies, or thereabout. Alright? So the system will keep sharing energy, there's the energy, and it will keep sharing energy until its multiplicity is maximized. That's just what it does. And the multiplicity is maximized when there is an equal amount of energy in all the bodies in your system. Alright? And that's what equilibrium is. So that's what we saw when we did our both our Einstein solids and our ideal gases. But what does that mean? Well, that means heat has flowed. Let's say that the multiplicity of B was greater than the multiplicity of A to start. And so was the temperature. The temperature, or the amount of energy in B, was greater than the amount of energy in A. So we saw that the system finishes, stops or is most likely to be in a system where Q sub B is equal to Q sub A, which is equal to half the total energy, where Q total is equal to Q sub B plus Q sub A. And I know you can just about see that. Well, that makes perfect sense. That the total energy is the sum of the energies in A and B, and the system will stop when it's half the energy is in both. Now, what about the multiplicity? Now, I won't talk about the multiplicity of A versus the multiplicity of B, but what I will say is that the total multiplicity will have increased. And well, maybe not increased, but the total multiplicity is now maximized. So there is half the energy is shared when the multiplicity is maximized. So heat is flown. Now see, there's heat in B was hotter, but it's in equilibrium when B is equal to A. So B is after getting colder and A is after getting hotter. So heat is flowed from B to A, or heat is flowed from the hot body to the cold body. That's what, and that we call the second law, heat flowing from hot to cold. Simple. But we can say, we've mathematically seen that heat flowing from hot to cold happens because the multiplicity has increased. So the multiplicity of our bodies, or our system, tends to increase. And the physical result of that is that heat is flowed from hot to cold. So really what we're saying is that the second law of thermodynamics isn't a real physical law. It's more of a statement of probabilities. It's ridiculously likely that the system will settle in its most likely macro state. The most likely macro state is the one where the energy is shared equally between all your bodies. And that's when the multiplicity is maximized. And in order for the multiplicity to be maximized, the heat has to flow from the hot body to the cold. So then you might ask yourself, just as an aside, well, what's stopping heat flowing from cold to hot? Why can't we have heat flowing from cold to hot? You know, people will say immediately to you, well, that will violate the second law of thermodynamics. Now, we've just said that the second law of thermodynamics isn't a physical law, it's more of a statement of probabilities. So is it impossible from heat to go from cold to hot? Is it impossible? I don't know that I can really answer that question, but I will say that the probability of heat going from cold to hot is virtually zero. Okay? But heat flowing from hot to cold is virtually the maximum. The probability is virtually 1. Alright? So just to say it once more, okay, I'm probably labouring the point. The multiplicity, if you were to draw it from here, we'll say this is the end of my Gaussian. Even into the center, to draw it on paper would take thousands of kilometers. Just to draw a Gaussian, which is on paper, let's say a centimeter. Okay? But the system will be in this. The system is most likely to be in this particular in this particular state, and we found that particular state is half the total of energy. And if we plotted Q sub A, it'll be that way, or if we plot Q sub B, it'll be that way as well. Alright, so for that reason, heat isn't going to flow from cold to hot, because let's say, if we're to look at let's say there is the energy in A. Well, where is hot? Well, this is hot, and this is cold. Okay? So it's the probability of the system being colder is zero. The probability of the system being hotter is zero. And I'm sure you can hear a bit of a vehicle moving out the back there. Alright? So I'm going to finish up. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.